So now we will continue the lecture from the last week. Okay, so sorry about the technical problem. So we have been talking about the count drive actuator starting from last week. And just several things to keep in mind, several important things. So the actuator is like a capacitive type actuator. So the two plates, they overlap with each other, okay, without any contact. So the fundamental things are we can consider this a capacitor, and you apply voltage across these two plates, and the energy will be stored inside the capacitor. So when you are doing the actuation, actually the energy status will change, and also the force. Okay. So for the operation mode, we have two different modes. One is we call lateral driven. Lateral driven means we move the plate horizontally, okay? Keep the distance the same, okay? The other one we call the gap closing. The gap closing means we move in the Z direction, keep the overlap the same, okay? And also we have two different operation mode. One is we call the constant charge mode. The other one we call the constant voltage mode. For constant charge mode, that means after we charge these two plates, we take out the battery. So during the operation, there is no battery connection. Only the two plates stored with the energy originally applied into the system. So, so during the operation for charge, constant charge mode, so we have found the equation we developed last week. So we can find out from the constant charge mode, when you move in Z direction, okay, the force is constant, okay? Because when you move in Z direction, the charge status on these two plates, the density won't change. That means the force are the same, okay? Force will not be changed. But in constant voltage mode, that be different. Constant voltage mode, we connect battery onto these two plates. So when you move the plate, actually the charge status will change as well, okay? So if you apply the constant voltage mode, you can find out if you move in the X direction, the force is the same. The force does not change, okay? So keep in mind, in constant charge mode, you can move in Z direction without the force change. But in constant voltage mode, you can move in the X direction. The force does not change. Okay? Is it clear? Easy to understand? Okay? So the important, the energy and also the capacitance part I have mentioned last week. So now we will go to the real design, combine the capacitor with the spring system. Okay? The spring system. So because we want to suspend all the actuators without contact with the bottom surface. So when they move, they definitely need something to support them, okay, without contact. So the supporting structure is the structure shown here. Those structures are the spring structure. So you can, actually those springs is made of like a cantilever, okay. So remember in the accelerometer design, the cantilever move up and down, right? Okay, but here we move laterally, okay? The deformation of the spring move laterally instead of up and down, okay? So the count drive will be applied when we apply voltage to one of the stator. So the count will move toward that direction. So when we take out the voltage here and apply voltage on the other side, we can move toward the other side, okay? So, so when we apply both of them, they can move back and forth, okay, freely. Okay, so the suspension will be only the spring over here. So the anchor position is these are two dark area. So only these two dark area contact with the bottom surface. And the spring over here and also the column over here are suspended above the surface without contact, okay? So now we will consider, after you understand the actuation mechanism, now we will go forward to take a look of the design of the spring system. Okay, so because the spring system is based on the cantilever beam, so we will come back to cantilever first. Okay, so we have talked about this last week. Okay, the spring system. So now we rotate the whole actuator 90 degrees. Originally, it moved this direction, right? So now we move 90 degrees. So now the actuator will move up and down, okay? The vertical direction, okay? So we arrange the spring first in very simple version, a very simple support, okay, very simple support. So only one cantilever beam connect to the actuator. So for the cantilever beam, actually we developed some equation. So the cantilever beam, actually, if you consider only one single cantilever beam, okay, and then move top and bottom. So the spring constant can be considered as EA3B over 4L3. We developed this equation like 1 month ago, okay. So so the spring constant we define as if you apply some force and what kind the deflection you will have. So you divide the force by the deflection. You find out a constant. This constant we call the spring constant. Okay. For cantilever beam, the spring constant will be proportional to the A cubic. The A cubic means if you move in this direction, the thickness of the beam, called A, okay, will be dominantly to decide the amount of spring constant. So if a very thick beam, very thick A here, you got a very high spring constant, okay, because it's a cubic, okay, and the depth of the beam B affect only in the first order. It's not the third order. So the thickness is more important than the width of the beam. And also the length is also important. So if you have a long beam, okay, very long, large L over here, so it also will reduce your spring constant as well, okay? And there's L cubic over here, so it's pretty effective. So as you have done in your second homework, I think the past homework, less homework. The less homework, you try to adjust the cantilever beam, to adjust the frequency response and also adjust the responsivity, okay? I think the most effective one is the length of the beam, okay? So here we will adjust the length as well, actually, because it's hard to adjust the thickness, the width, and also the thickness of the beam. So you can do a little bit, but the most effective one is the length, okay? So once you have one cantilever beam, okay, now we consider back this situation when we move the center part toward the top, either toward top or toward bottom. So the cantilever here will be deformed on two sides, okay? So the deformation will looks like this. So, because we have fixed walls on either side, right? This is the center part, and this part connect to the actuator. We take out one side, for example, left-hand side, for consideration. So put this one here. So when the whole actuator moves down, okay, you can see the cantilever will deform like this. Because on this side and this side, that means this side and this side, you consider there are two walls over here. So the cantilever at these two sides won't deform, won't deflect. Okay, so so the position will be the same, and also the slope will be 0. No slope, it's not inclined. Okay, so the cantilever beam at the end always perpendicular to the wall. Won't change the angle. The angle is 0. Okay. So if you consider deformation like this, so you cut from the center part. The center part is a refreshen point. the reflection point means you change the slope from one slope to the other. Originally, you have a slope gradually increase. Then at the reflection point, the slope start to reduce. Okay, the amount of slope start to reduce. So the center part we call the reflection point. So if you cut through the reflection point, you can find out this kind of cantilever can be considered as two original cantilever combined together, right? So if you have a deflection pushed down, so the deformation of this cantilever will be similar to this one on the left-hand side, right? And then the bottom one, you just flip it over and make it as a mirror. So you can find out this cantilever, actually the deformation is similar to the other one, right? So now you have two spring. If you connect this way, when you apply the same force F, you find out the deflection will be doubled, right? Originally, you have one cantilever, the deformation will be Y1. Now you connect the other cantilever with the same force. So total deformation from here to here, okay, from this position to this position will be twice. So this kind of connection, spring connection, we call it is like a series connection. When you connect two springs seriously, the deformation will be doubled. Okay, when they are under the same force. So that means the spring becomes softer, right? You apply same force, but you got a double of the extension. That means the spring becomes softer. Okay? Is that easy? Okay? So that means when you seriously connect two springs together, the spring becomes softer. Okay? So in addition to you change the length. Another way to make the spring softer is by series connection. Okay, series connection to make the extension, the deflection, much more. Okay. So now we consider the original length L give you this kind of spring constant. So this the new type of spring, what kind of spring constant it will have. Okay. So we consider back this equation. So for this kind of spring, you have two similar springs series connect to each other. Each spring, the length will be L over 2, half of the length. Suppose we have a total length the same. Okay, this spring has a length L. The second spring also has a length L. So we cut it into half. So half of the spring have the length of only L over 2. Okay, half L. Okay, so if your spring, the length have half L, so spring constant will increase how much? 8 times, yeah, correct. Because your L become L over 2, so the total spring constant will become much harder because your length becomes shorter. So the spring constant here will be like 8 times of spring constant of K0, 8 times. If you consider only one spring here, will be 8 times of K0. Okay? Now, if we connect these two seriously, okay, so the spring will become softer because the deformation will become twice. Okay? So originally you have 8K0. Now you reduce the spring constant by half. Okay? So the total final spring constant will become 4K0. So the process is original you have the length reduced into half. So you have 8K0. Then you connect the two springs seriously. So 8K0 need to divide by 2. So finally, you have a spring constant 4K0 by arranging the spring in this kind of situation. Do you understand? Okay. So from the equation, will be easier to understand. So we call this a new spring constant will be the K1 spring constant, K1. So the K1 will be, you give the same force F, but you got twice of the deformation, right? 2 delta Y1, okay? And F over I delta Y1 will be using the equation, the K equation, the spring constant equation. But you apply L into L over 2 into the equation here. So you bring this equation and put the L into L over 2 over here. So you end out, got this value will be AK0, right? This part will be AK0. So AK0 divided by 2, you end out, you got a 4K0, okay? So if you arrange the spring, okay, deform at the two ends clamped. Clamped means the slope will be 0, the position will be fixed. So in this case, the spring will become harder, okay, stronger. The spring becomes stronger. So it's 4 times stronger than the original one. Okay, so this is the first step. So first step, we consider only one spring. However, when you look back into the design of the cone, okay, here. So it's not only one spring over here. You can see 1, 2, 3, 4. 4 springs connect to each other, right? Okay, so so we need to think of if we do different arrangement, what will be going on. So now we have only one set. Now we have 4 sets. So we need to consider further, step by step. Okay. Okay. So the first step, we consider only one spring, one cantilever. So you got the 2 fixed end and the deform at the center. So this we got a 4K0. Okay, K0 means that you have only one cantilever and the defect at the end. Okay, now we change the situation from this situation into this deformation situation. So the spring become harder, become stronger, become 4K0. Now we consider, we connect the two this kind of spring together, okay, seriously. So we call this a crab leg. It's like a one pair of crab leg. So the crab leg, again, is considered 2 similar springs connect to each other seriously. Okay, it's a serious connection because when you apply the same force, you got to double the deformation again. So it's a connection, it's a serious connection. So for serious connection, so the second spring constant K2, okay, series connection become 1/2 of the K1, okay, become even softer. Okay, so the spring constant become 2K0. Original the K1 is 4K0. So the crab leg will be softer, okay, than only single. You apply only single spring here. So you have a 2 spring over here. You got to double the deflection. So the spring becomes softer. So the spring constant changing from 4K0 down to 2K0. Okay, is that understandable? Okay. Now we consider, okay, the total structure of the beam. So we have 4 legs, okay, not only 1 or 2. So now we consider we have 2 these kind of things connect to each other, okay? Okay, so now the connection it become not serious, it become in parallel. That's 2 springs. That means if you make another crab leg to the other side and then connect to this one, okay. For example, this crab leg is only this portion, the bottom portion. When you take a look, it's the bottom portion. So the bottom portion give you 2K0. But now without more deflection, but you add another spring in connection with the original spring. The deformation is the same, deflection is the same. but you have another spring to connect them together. So this connection will be in parallel connection. It's not series connection. That means we apply the same force, but we have two exactly the same spring to share the force at the same time. Okay? So each force will become half. Okay, if these two springs, one is on the bottom, the other one is on the top, they share the same force. So each individual crab leg will have the force on them only half force. So you have half force. That means the spring becomes harder, becomes stronger. So the folded beam, and finally folded beam will become 2K2. Will be the 4 times of the original spring constant, the folded beam.